Okay, guys, so let's get started. We'll finish this chapter today and I'll open the test. That's the goal today. Okay. So let me remind you, this chapter is about fossil fuels, and I'll briefly go over how you make oil and gas and coal. Okay. Oil and, as you saw, oil and gas are made from microorganisms in the ocean. Okay. When these drop to the ocean floor, they have to be in an oxygen-poor water. If they're in an oxygen-rich water, they'll get recycled. Okay. And then they have to be trapped by clay. So you drop organic matter on the floor, and then pour clay on top of it. Okay. So, for instance, when a river comes in, when the Mississippi River comes in and all that, it brings in a lot of silt and all that stuff, and you bury it under silt. And now, over the next few million years, 50 to 100 million years, what you try and do is, on this organic matter, you put pressure and warm it. As you go deeper, the temperature rises, so that organic matter has to be treated to pressure and temperature. Yep. That organic matter turns into something called kerogen. Yep. And that is the raw material for oil and natural gas. Okay. Now that kerogen has to be subjected to, if you subject it to a temperature of something between 90 and 160 degrees, then you produce oil and natural gas. Okay. Above 160 degrees, it's all natural gas. And natural gas and graphite. So we saw that. Okay. And again, how do you raise the temperature? Again, you have to, so this silt is building up, and this didn't happen overnight. How long did it take for that silt to build up? Millions of years, 50 to 100 million years. Okay. This is about 2 kilometers deep, 2 to 3 kilometers deep. It's from here to US 1. That's how much silt is built up. Okay. All right. So let's say that kerogen has been subjected to 120 degrees Celsius. It's become oil. Now oil is less dense than the surrounding stuff, and it'll rise up. Okay. Where does it rise up to? Where does it stop? So it'll keep rising till it hits a rock which it cannot penetrate. Okay. So, and that'll be the oil reservoir, and I'll show you a picture in a second. Okay. So that's where you find oil and natural gas. Okay. All this happened in the crust. Okay. And you saw that. So again, we talked about this. The radius of the Earth. Anybody remember? Is 4,000 miles. Okay. And the top 1%, for about 40 miles, is broken up into plates, and these plates are, so oil and natural gas are over there. All this is happening. These plates are constantly moving, and so for instance, these plates will move about in 100 million years. They'll move about 4,000 kilometers each. And if this plate moves in this direction, that place. So in 100 million years, if an oil deposit happened here in Florida, in 100 million years, this plate can move to Paris. Okay. So that oil and natural gas always forms under the ocean, but over time it'll it starts formation in oceans, and then over time it can be transported. Okay, did you guys understand that? All right. All right, so let's make coal now. To make coal, you need forests. Okay, and this dead matter gets in swampy regions, and then gets buried with clay and silt. And then you add pressure and heat over millions of years, okay, and it eventually becomes high quality coal. Okay. This is the best quality coal. This is poor quality coal, better quality coal, better quality coal. What makes it a better quality coal? This has moisture. Half of it is moisture, water. Okay? And our pressure and heat treatment, the moisture content decreases. Okay? And what you want is more and more carbon. Okay? The first forests were 250, 300 million years ago. Okay? And that is the oldest coal. Okay? And all right, so we learned all of that. And now, why do we use fossil fuels and not wood? It's this energy density. Okay, and that's a very important thing to remember. So, what this diagram tells you is the amount of energy 1 kg of this material has. Wood has 10 megajoules of energy per kg, and look at this. Coal has 30 megajoules per kg. Okay, so 3 times the energy density. So, for instance, right now in electric vehicles, that is the key thing. Energy density of your batteries. How much energy can you pack in the battery? Why does it matter?
For efficiency?
More energy you can pack in, the lighter the car is, and the less energy you'll use to transport it. Right, so energy, and right now you can't make airplanes flying on batteries. Yeah. Yeah. So, but if you had high energy densities, you could eventually get there. Okay. Oil has 4 times the energy density of wood, and so on. And natural gas has 5 times the energy density. Okay, except that natural gas is hard to transport. So you can transport it through pipes, but you have to find it on land to transport it. Okay, so we learned all of that. All right, so here's a oil deposit. See, here's the impermeable rock, meaning oil can't penetrate through there, and here's a porous rock through which oil will rise. I guess so. This is where you generally find oil. Here's water, and you'll have a layer of oil on top of that, and then natural gas on top. Okay, and this is from, you find these reservoirs from to a depth of 3 to 4 kilometers from here to the beach. Okay, so the oil reservoir will be that far away, and then you dig and find that. Okay, when you first drill, this oil will rise up on its own because it's under pressure. 10% of it will come up. Okay, so when oil is drilled initially, underground pressure forces the oil up. About 10% of the oil can come up. Additional recovery is achieved by injecting water into the reservoir and increasing pressure. Okay, and then there's oil in the rocks. Still, you want to extract that oil. Now, to make it flow, you inject steam and other materials. Okay, some polymers are used to force oil out of the reservoir rocks. Okay, you saw that even with all the methods used, only about 50% of the oil is extractable. Okay, so if there was 100 gallons of oil in the reservoir, you can bring up only 50 gallons.
Why is that?
What's that?
Why can't we take all of it?
So it's mostly in the porous rocks, and you can't make it flow.
Right. So it's just stuck there?
It's just
So
stuck.
it's ready to come back up?
No, it's just stuck there.
Oh. Is that why we always have to move the oil wells when they're just draining? You have to move them, right?
You don't move them. You once you pump all you can pump out, then it's dead.
So
Then
the rig itself is just left there?
I don't know what,
Oh.
but you can't do anything more. It's done. You've squeezed it dry.
Mm-hmm.
Okay. Now you got to find new resource, new wells. All right, so 50% is the best you can do. Okay. You saw that oil has many components, heavy components, and cracking is just so. Do I have a picture of a hydrocarbon? Okay, I don't have a picture of hydrocarbon. Okay, so cracking is you. So this is a long chain hydrocarbon. And you can see why it's called a hydrocarbon. This is a particular organic compound called an alkane. And they name them depending on how many carbon atoms there are. Okay, so one carbon atom, that is methane, two carbon atoms, that is ethane, three carbon atoms, I don't know what it's called, 8 carbon atoms is octane, and so on. Heptane, pentane is five carbon atoms, and so on. Okay. Cracking is, this stuff is heavy and not useful, and you just heat it and crack it. Okay. So that's the process. Gas, to optimize the use of petroleum resources, it's necessary to convert some of the less needed refinery products to more. In most cases, this involves breaking down heavy hydrocarbons like tar and paraffin to make lighter hydrocarbons like octane. So this involves heating hydrocarbons to a high temperature to break the chemical bonds. Okay. All right, now we'll come to natural gas. So how's natural gas formed? Again, microorganisms in the ocean. And you have to treat kerogen to between 90 and 160 degrees. Then you get oil and natural gas, and above 160 you also get natural gas. Okay. So here is a tight sand gas, oil, and natural gas associated with an oil reservoir. Okay. Here's another natural gas reservoir without oil there. Okay. So formation of natural gas is less efficient than formation of oil, and it's only about 0.1% of the carbon. So what that means is if you're making natural gas from plankton microorganisms in the ocean, and for every 1,000 carbon atoms that you started off with in the microorganism, 1 atom ends up in the natural gas. Okay, so that's what that number means. Okay, so for every 1,000 carbon atoms in the microorganism, 1 carbon atom ends up in natural gas, which is mostly methane. Okay. All right. So here are the natural gas resources in the world. Okay. So you see that Russia has a quarter of the world's natural gas resources. Okay. And this is in billion cubic meters. So this is roughly a quarter. Well, this is a quarter, so the full amount is 200,000 billion. All right, now again, why do we use all these fossil fuels? What do we do with it? You take the fossil fuels and you burn it. When you burn it, you're combining it with oxygen, okay? And carbon dioxide and water vapor are the products, and energy, okay? And again, any time when you burn and you get energy, what that means is the products weigh less than the ingredients. When these guys weigh less than these guys, then you get energy. If these guys weighed more than this guy, then you would have to put energy to make this thing. Okay? Anyway, burning just means combining with oxygen. Okay? So natural gas, when you burn natural gas, you get 55.5 megajoules of heat per kg of natural gas. Okay? So Russia transports its natural gas to Europe. It sells a lot of its natural gas to Europe via pipes. and those pipes go through Ukraine and all that. Yeah. But over land, that's easy to transport. But let's say if Russia wanted to sell its natural gas to Argentina, what do? You have to liquefy the natural gas. You have to turn it into a liquid at a low, and that happens at a low temperature, very low temperature, and then transport that. So you can sell natural gas to Argentina, except that now it's a little more expensive. Okay? Transporting it. I gotta get this fixed. Okay, so you could liquefy natural gas and transport it, except that it makes it a little more expensive. Okay. Natural gas is easily transported over land through pipes. Okay. Fracking, you guys have heard of fracking? Okay, so again, this is, see, look at the depth of this. This is 2,500 meters. That's from here to the beach. Here's a shale rock, and there's natural gas in the rock, trapped in pockets in the rock. Okay. After you brought up all the gas, brought up gas that was free in a pocket, then what you want to do is, okay, so I'm just going to draw a small picture. Here are little pockets in the rock that have natural gas in them. Okay. How do you bring this natural gas out? What do you think you can do?
Stick your pipe down there.
Well, okay, you stick your pipe down here. If you hit this pocket, you can get this. What you do is, if you crack the rock, all this natural gas will become free, and then you can pump it. That's what fracking does. Okay. So fracking, hydraulic fracturing, is often used to enhance natural gas recovery. Water with chemicals added for various reasons is injected into wells under pressure to fracture the rock. You're fracturing the rock and allowing the gas. So you fracture this rock, all the gas is collected, and it'll enter the pipe. This technique is controversial because of potential contamination of water supply with fracking liquids. But we've been doing this since the 1940s. Yeah. So coal is formed much as oil and natural gas. So oil and natural gas are formed from microorganisms. Coal is formed from plants. The earliest extensive plant growth occurred 350 million years ago. Okay, so the oldest coal deposits are about that old. Coal exists in several varieties depending on the age and formation conditions. Okay. The oldest and the hardest coal is anthracite, which has the highest carbon content. So this has the highest carbon content, and it's the oldest coal. Okay? And again, all these coals have more and more moisture content. Okay? So again, you take plant matter and subject it to heat and pressure. Typically, younger coals are softer and have lower carbon and higher moisture content. So here's a list. So anthracite is the oldest, bituminous next, subbituminous, lignite, and look at the moisture content. The hardest content, moisture content is only 10%, okay, and lignite is 45% moisture content. And that translates to energy content, okay. Again, what is it that you want? More energy. Energy density is what you're always looking for, higher energy density. Okay? So anthracite has 35 megajoules per kg, and lignite is only 14 megajoules per kg. Did I show you that electricity generator?
Mhm.
Okay. So what do you use coal for? So 70% of the coal is used for electricity generation. So what you do is you burn the coal, produce steam, and then you're turning that generator.
It
Right?
doesn't, this, the bottom part of this bill, but just Coke.
Oh, okay. So coke is made by heating coal to about 1200 degrees Celsius in the absence of air. So volatile materials are driven off and pure carbon is left behind. So this is in powder form, it's like soot, and that's used in production of steel. Okay. So those are the two main uses of coal. Okay. Let's see. Electricity generation is 70%, coke production is 17%. Okay, so that's almost 90%. Okay. And the rest is exported and yeah. So, all right. Over half the U.S. coal comes from the Appalachian region. Okay. However, coal from Midwest and West have low sulfur content. So the Appalachian coal has a higher sulfur content. Why does that matter? Because when you burn sulfur, you turn it into sulfur dioxide, which turns into acid rain, sulfuric acid when it rains. Okay. But the Midwest and West coal is better, except that it's in a sensitive area, in the Rockies and stuff like that, and nobody wants to dig there, or they don't want you to dig there. Okay. Coal occurs in seams of beds varying in thickness from inches to more than 100 feet. So you could have a vein of coal as big as that big building 100 on campus. Okay, so imagine a vein that big. Okay, so you can see that here. Okay. Coal mostly is produced from strip minings with seams close to the earth's surface. Okay, so this was sort of near the surface, and you remove the topsoil and dig for coal. Okay, the removal of, and this is an energy and environment class, and the reason it's named that way is most of our environmental problems comes from fossil fuel sources. And the biggest problem being, what is the biggest problem? Climate.
Carbon.
And why is that happening?
Because we're releasing too much gas into the air.
Which one specifically? This guy is the culprit.
Carbon dioxide.
Yes, so that's in a nutshell. And what is your generation going to do about it?
Hopefully fix it.
Yeah, how are you going to fix it?
With wind and
I
solar.
don't know.
Okay, so if the world runs on renewables, then that won't be an issue. Yep. Okay, so So we were doing strip mining. The removal of topsoil and vegetation in strip mining leads to erosion. The exposed land is not capable of supporting vegetation. Yeah. So coke use in the US, 70% is used to produce electricity, 20% for coke, which is used in steel production. Okay. Carbon dioxide causes climate change. They used to call it global warming, but now the politically correct term is climate change. All right, so here are the Hubert graph for worldwide coal production. Yes, so what this Hubert graph says is for any resource like oil, gas, or it could be any resource, any mineral or whatever. Okay. You first discover it, and its use will increase as the production methods get more and more efficient, if it becomes more economically feasible. And then the use will peak, okay, and then you've got to find new sources, which might be harder to find, and eventually you run out of all resources. Okay, so this is the Hubert peak, and it's turned out to be true for a lot of resources. Okay, so here is the Hubert peak, Hubert curve for coal. This is worldwide, and we haven't reached the maximum use of coal yet, and hopefully we'll never get there. Okay, but if we keep using it at the current rate, you would reach maximum, or the current, if you were to keep using it like you were using 10 years ago. Okay. China has been very aggressively pursuing renewable energy. Okay. Anyways, you would peak in 2060. Okay. The world still has about 1,200 years worth of coal, if at 0% growth. Okay. Again, however, we hope to stop using coal long before that. This is oil shale. Okay, so oil in pockets of the rock, and there's enough oil where you could burn, not burning the rock, you're burning the oil, but you can light up and it'll burn. Yeah. In the US, most of the shale that is rich in oil is found in the Green River area of the Rocky Mountains, and nobody is going to touch that. US has the most shale rock in the world. If you extract this raw oil, it costs about, some estimate is about twice the oil that comes from wells. But also this would have a huge environmental impact. In Estonia, they get a lot of oil from shale, raw oil shale. 97% of pollution in Estonia is because of that. Organic matter trapped in sedimentary rocks turns into oil over millions of years. You saw that. Some deposits are rich in oil that the rock can burn. Okay. So the Green River area has 600 billion barrels that can be recovered economically. The shale is mined, crushed, and heated to 400 degrees Celsius. So you get this rock, crush it. Yeah. In rich deposits, more than 30 gallons of oil can be extracted from a ton of shale. So a ton of shale would be about half this guy. Okay. And so there is enough oil in there where you could get 30 gallons, so roughly the same volume. So here are the shale oil resources. Okay, you see that we have the greatest shale oil resources. Almost all of the world's shale oil resources. And of these, we have 4,000 billion barrels. 600 billion barrels can be economically recovered. Okay. Good quality oil shale produces the equivalent of 100 liters per ton of shale. Like I said, a ton of shale is a ton is 1,000 kgs. Yeah. This is about 12% the energy content of 1 ton of bituminous coal. Okay, so even the second grade coal, shale oil only has 12% of that energy content. So here's the shale oil resources in the pretty part of the Rockies, and so nobody's going to touch them. Okay. A rock or honey trapped in a rock, and that's 3 kilometers below the earth. What do you think is easier to extract? Water. All right. How would you extract the honey? You'd have to somehow heat it to make it flow. Okay, that's the problem with extra heavy oil. Okay. Extra heavy oil has a very high viscosity, and it's more difficult to extract. And Venezuela has almost all the extra heavy oil. Okay, you see 2,000 billion barrels. Commercial extra heavy oil production has been going in Venezuela's. Tar sands, you can see that. So here's a sort of heavy oil and sand, mixed in sand. Again, how do you extract it? You mine this thing and pass steam over it. To recover the oil, the sand is mined and mixed with hot water or steam to extract the bitumen. Yeah. Pressurized hot water can be injected into a well, and after some time, the bitumen water mixture is extracted. Canada has the largest source. Okay. And again, all these sources are much more expensive than the oil that's pumped up in Saudi Arabia. Again, there you just have to pump it up. That's nothing. Yeah. So world tar sand resources, Canada has almost all of it. Okay. Canada has been producing oil from tar sands since 1967. So this is lifetime of resources. Yeah. What we'll mention is how long will all these resources last in the world. Yeah. So again, United States, Canada, and world. Lifetime of oil resources for different growth rates. Okay, so this is 0% annual growth rate, meaning you're not going to use more and more. Okay. The U.S. has 45 years worth of, and these are figures from 2007, so from the textbooks, it's older figures, but 45 years, subtract 20, so about 25 years worth of oil. Okay. The world has about 50 years worth of oil. Okay. The use of oil has been decreasing in the U.S. over these last. Okay. Okay. In the world, the use of oil in that period has increased by about 2%. Natural gas, 0% annual growth rate. There's 35 years, so about 20 years more left. Okay, at 5% annual growth rate, we'd have already run out of it. Okay. Coal resources. Okay, the world has, if there's 0% annual growth rate, there's 1,200 years worth of coal left in the world. Okay. So you saw that all fossil fuels are produced by subjecting organic matter to temperature and pressure. How do you apply pressure and temperature? You pile it up with sediments and bury it underground. Does that happen overnight? So you're burying it over 50, 100 million years. Okay. Crude oil can be refined to yield a variety of products. natural gas is 85% methane and 15% ethane. Okay, methane is CH4 and ethane is 2 carbons. So this is natural gas, 85%, 15%. Coal has different ranks depending on the formation conditions, okay, and the moisture content. Anthracite is the best coal. It has the highest energy density. Worldwide oil production is approaching the Hubert peak. In the US, the peak was passed 40 years ago. Coal has the greatest longevity. Shale oil is plentiful resource, but is not economically viable at this time, and also environmentally very costly. Okay. All right, guys. So